explicitly done here. I have written K instead of J. I have kept in the equation which I have written, if you see, J doesn't appear in the equation at all. It is K. The reason is that I want you to write a similar equation for J. With just replace I by J, keep K is the same. And then you do this. Because otherwise, if you may end up, if you don't do it properly, having 3 J's in the same term, which is wrong. So that is why, so this is just given to you. You try it out at home, do it in a fair way, but keep the answers, and we will continue this assignment as the semester progresses. Because we'll from here, I'll first give the name to some of these terms. So next assignment which I give you, I'll give you the answer of question 3. The third question or fourth question, whatever that is here. Question 3. So I will give you that answer. We start from there and there we'll derive the equation for kinetic energy. But try to do this by Monday because this was already given to you. So this, I think you should be able to do it. And that you don't have to submit it. Keep it with you. Final submission I will take later. तो वो अभी सबमिट कर दिया था, ठीक है. You have done your job. I have not done my job. I will, but we'll discuss that sometime later, even if I don't grade. I was thinking I'll grade and then discuss, but if that is not there, then I will discuss it later. Okay. So now we will, last lecture was lecture 11th. In the last class, we were talking about, again, some estimates of the velocity fluctuations. And I think the best sort of takeaway from that we will take, and then we will move on. So I'm going to skip a bit of some parts of the textbook. But basically what we say is that when we are now talking of turbulence, in turbulence, when we talk of scales, then we have if u1 prime, u2 prime, these are the velocity fluctuations, then what we find is that u1 prime and u2 prime are well correlated. And this is as opposed to the laminar flow where we said that if there is any oscillation about the mean or oscillation of the flow, then the fluctuations are not well correlated. And this correlation coefficient is something like of the order of 0.4 or 0.5 is the correlation coefficient. And this coefficient we define as C is equal to the mean velocity of u1 prime this square root of u1 prime square, this is the RMS of u1 prime, and this is the RMS of u2 prime. What do we mean by RMS? Root mean square. So we are taking the square of this. So obviously square of u1 prime will not be 0. It will always be positive. Even if u1 prime is fluctuating, it has a 0 mean. But u1 prime square at each realization will be positive. And when you take their mean, it will not be 0. So this square root of u1 prime square is what we call as the root mean square of u1 prime. And similarly, if we do that for u2 prime, that's called the root mean square of u2 prime. And this is how the correlation coefficient is defined. And this correlation coefficient, what we are saying in turbulent flow, is not small quantity. It is something of order 1. So it's 0.4 for many flows when you work it out. And one can see some of these. Okay. So this is the correlation coefficient. And then what one does is, and also what you find is, I will use u1 prime RMS for RMS of u1. Because since we are using prime for fluctuation, in Lumley's text, he doesn't write the subscript RMS. Because there the small letter is used for the fluctuation. But this makes it very clear that we are talking of RMS. It's not the fluctuation. So u1 prime RMS is of the same order as. Now realize this. How will this fluctuation graph look like? A velocity fluctuation, if I plot it with time, then this will be something which will vary about the 0 mean. So it will fluctuate about 0 because these are fluctuations. So their mean has to be 0 by definition. Okay. So what we find is that because these are well correlated, so these two RMSs will be of the same order. So let us say in a particular flow you find u1, if mean of u is 10 meters per second, then maybe u1 prime is something like 2 meters per second. u1 prime RMS. So u2 prime will be also of the same order. So it can be, if it is 2, so it could be 1.5, it could be 2, or it could be 2.5, but in that same magnitude. Okay. So this is what we have. So now if we try to look at the Reynolds stress term, which is so if I try to find the order of magnitude of the Reynolds stress term, this will be rho times u1 prime, u2 prime average, and each of these in RMS is u1 prime square root of u1 prime RMS square and square root of u2 prime RMS square. So this will be equal to rho times, I've written it as u2 prime, it could be u1 prime also. But we call it u2 prime because we are generally seeing the transport as the vertical one. So that's why. So it's equal to rho times whatever is the RMS square. So this is what the Reynolds stress is. And if we try to look at the fluctuating component of the vorticity.
Sir?
Yeah.
Sir, we took point for correlation coefficient. It was just as an example, or if we say very correlated?
No. So that was just in the typical numbers which we find in flows is something of the order of 0.4 in the boundary layer. No, if it is much less, then they are not correlated.
If it is like 0.2, then?
No, 0.2 again, it talks of an order of magnitude. So 0.3 to 1, you take it as well correlated. If it is much less than that, let's say it's 0.1 or 0.01, then you will say. But as we saw in the molecular motion, this number turns out to be 10 to the power of -4. So that definitely is not correlated.
So this is an electron.
This is turbulent shear. We are talking of shear flows. Mean U1 is a function of x2. Okay. Now, if I look at the fluctuating component of vorticity, now vorticity, if you realize, is del cross, or omega I prime is del cross ui prime. So in vorticity, what you have is it is a cross derivative. So it will be something like partial u1 prime by partial x2 if it is one component of velocity, the derivative will be in the other direction, 2 or 3 direction, and they will give you different components. So typical vorticity component, which we write it, is something like this. And here, if L is the length scale of the turbulent flow, so the fluctuating component of vorticity will be equal to some scale in the fluctuating scale divided by the cross length scale which we are taking. And the point is, in the turbulent flow, this x2 is of the order of the eddy size, the largest eddy which is extracting energy from the flow. And that is the big difference, that this L, when we write the kinetic theory of gases, etc., and we do the next thing, then this is very close to the initial point. But in turbulence, up till the length of the eddy, there is a good correlation. So this scale is not small. So this vorticity, which we say, the fluctuating vorticity is equal to u2 prime upon L. But we also know that the fluctuations are maintained in a turbulent flow. The fluctuations come because there is a mean shear. If the, or I should specify, not turbulent flow, in a turbulent shear flow. If the shear term is not there, the turbulence will die. The fluctuations will eventually, if there is no constant source of energy to the fluctuations, they will die, the flow will become laminar. So, because the fluctuations are maintained due to du1 by dx2, one can equate the two scales in vorticity, scale from du1 by dx2 and u2 prime RMS upon L. And this gives us u2 prime RMS upon L is equal to some constant times du1 by dx2. And what this implies is, and this was the assumption we had made, that the time scale of the eddies is the same as time scale of the mean flow if there is no other characteristic length. C3 is just some constant which is of order 1. I just put it again. You will see, if you read Lumley's chapter, these constants keep on floating, C1, C2, C3, C4, and everything in the end he makes them as 1. Because we are talking of an order of magnitude. So, and this was the precise we had used earlier, that the time scale of the eddies which are there is of the same scale as the time scale of the mean flow. And so that is why we have small l, capital L, I'll just count, and the mixing length are of the same order as and this capital L which I am talking of here, this script L which I have written, this I had defined as the ratio of du1 by dx2 divided by d2u1 by dx2 square. And the point here which comes is that this length scale is not small in turbulent flow. And that is why neglecting those terms which we had done earlier does not work. And that is why in the laminar flow we got the correlation coefficient as very small, but here it is large. So we cannot do that. And so, but all this here is working if there is only one length scale. If there is, and we will see, or if there is only one time scale. If more scales come, then you do not know which L do you take here, or which length are the size of the eddies of. Are they of the mean flow scale, wherever the variation which is taking in the mean flow, or of the second length scale if that exists in the problem. And that is why, and we will show this using an example right now. This looks like but see, if you recall, so what we have done is that Reynolds stress now, if we work this out, this will work out to be equal to rho times and this term is what becomes as the eddy viscosity. The u2 prime times L, that means a velocity scale times a length scale. And now, in early texts on turbulence, there is a model called the mixing length model. If you study turbulence and look at any text which is a classical text, almost everything starts with a mixing length model. And in a mixing length, there are two ways of how, and this was given by Prandtl, and he gave a mixing length formula. And what he said was that the eddy viscosity, nu T, or the eddy viscosity was equal to and Lm was defined as the mixing length. Yeah.
Could you please say how did you write the Reynolds stress and rho? Like how did you write this?
Oh, this is how we define the Reynolds. This right part, the second part, or rho u prime v prime. This rho u2 prime L. So this follows from what we have done earlier. If we write it as rho u2 prime RMS square and u2 prime RMS is equal to C3 L du1 by dx2 from there, okay? That's it. So now there are two ways how we can define. One is writing it in, so see, this is how classically Prandtl defined the mixing length. That nu t was given as a mixing length square. Or he defined the eddy viscosity is equal to a typical length square of the flow square times du1 by dx2. That means it has to be a shear flow where du1 by dx2 exists. There is no buoyancy or anything like that in this flow, otherwise this term will not come. So, or if a buoyancy is there, then you define a du1 by dx2 based on buoyancy and then use it. But this is how the eddy viscosity was defined. And what we also find is that this nu t in this turns out to be equal to C times, and this C is again just some constant RMS times L. I think this is what you were asking. What is it, this or is it this? Is that what you were asking? Yeah. So rho u prime v prime. If see this density, don't bother. If I write the Reynolds stress as u prime v prime, rho will not come. If I write it as rho u prime v prime, then rho will come. See, Reynolds stress, if you technically look at the equation, it turns out as rho u prime v prime. So if I use a rho in that definition, a rho will come in the right side. If I write the Reynolds stress, as many people call it, just as u prime v prime or u1 u2, so then rho will not come. If the rho is the question.
In this formulation, it would be rho v prime.
So that keep that in mind, that if I'm just saying u prime v prime, then rho will not be used. If I say rho u prime v prime, then rho will be used. So, and again, this sort of a thing would come because I'm trying to get you things from more than one texts. Yeah. The C is again some constant. Constant of order 1. So the C again, you will see these C's floating around throughout in the, sometimes I've called it C1, C2, C3, C4, or product of these two is 1, but these are of order 1. So the C is, so if you use it as, so it's some constant C. So maybe I call it C nu t or whatever. And then, see, the reason why Prandtl's mixing length became a successful model was that what Prandtl did was, he talked of a mixing length, he prescribed. So now in this, when you are using this model, you have to prescribe what is the mixing length. Okay. So sometimes you say the size of the eddy. Now what is the size of the eddy? The size of the room. So you put that. Or as we will see when we talk of wall flow, we use a different mixing length. So Prandtl put this in and he put it in the mean flow equation. So in the mean flow, the Reynolds stress is written as nu t times du1 by dx2. So therefore, when you put this, it will become nu t times du1 by dx2 means another product of du1 by dx2. And using this, he was able to get what we call as the log layer in the wall. Near the wall, there is a region where the mean velocity goes like log of y. And that we are able to get using the mixing length theory. And that's why the mixing length theory, at that time people thought will help us give the answers for turbulent flows. But it is very simple a model. It doesn't work for all type of flows. There also, so we'll see how this mixing length comes in a moment. How to apply this. Okay. So now let's apply this to turbulent flow near a wall. So these are some of the ideas that there is a mixing length. But then once again, all these ideas, if they work, they will work only if you have a single length scale and a single time scale. If there are multiple length scales or multiple time scales or multiple velocity scales, then these simple ideas will not work because you will not be able to define what is the mixing length. Okay, so these ideas work only if there is a single length scale and single time scale in the flow. Otherwise, it's a hopeless exercise. So now, let's try to take an example. And this is of turbulent flow near a wall. जो बाद में आए उनको दे देना ये शीट जो थी दे दी या बाद में. I have given you a sheet today, a homework sheet, please. If you don't, and I'll talk a bit about it later. So now let's look at a flow. We are looking at something like let's say the wall boundary layer. This is x1, this is x2. And we have some sort of a mean of u1 is a function of x2. Now here, so think of it as a notional flow. The pressure gradient when we typically talk of flows like this, then the flow is caused by a pressure gradient. Let's say if we talk of flow in a channel, then that's caused by a pressure gradient. There is a higher pressure and a lower pressure on the other side. But here what we are saying is the pressure gradient in the flow is zero. That means mean pressure is constant everywhere. But so then what is causing the flow? Very far away at x2 is equal to infinity, there is a wall which is moving with velocity u1 of I.
So is this go for passing through the origin?
Yes, it's passing through the origin. So flow is in the x direction. It is caused by something far away. There is a moving wall which is moving with u1I. So that is causing the flow. Is that clear? In the x2 direction. Flow is causing at x2 is equal to infinity.
So if it is far away, then its effects.
So its effects will come. It will. So that's why it goes to zero eventually. Okay. So at the flow anyway, the no slip effect has to be there. So it has to be zero. But also what we will assume is that this plate will consider two cases. One is when the plate is fixed and there are no holes. And the second case we will consider is when the plate is porous and we have some flow which is either going in vertically or coming out from the plate.
There are two plates like.
There are two plates. It's something like flow between two plates. The top plate is very far from the lower plate. So it's like a channel flow, you can think of it like that. So, and now at the wall, U2 is equal to Vm, and Vm could be positive or negative. Yeah. I think it's probably obvious, but so the top wall actually is not relevant except that it is providing some sort of a shear to the flow so that the flow is being caused. The top wall has been kept just for that purpose. That is what is causing the flow so that we can have the zero pressure gradient. If it is a finite channel flow, then typically it could be because of the moving wall or because of the pressure gradient. Okay. So now this is a turbulent flow we are talking about. That means if we look at it, so now the mean flow is stationary and homogeneous What this means is that mean flow in general will be mean of U1i plus mean of U2j plus mean of U3k. Now, we have a mean component U1 in the x2 direction that is given to us. That if mean of U1 will change with x2 because at the wall mean of U1 is 0. At infinity it is equal to whatever is capital U1, the value of the horizontal wall. Okay. Now, mean of V2 because Vm is there. So, there could be a mean value of V2. The y component of velocity could be there, but it will not be a function of x1 or x3. The flow is given to be homogeneous in x1 and x3. So, all averages in x1 and x3 directions are 0. So, mean quantities can change only with the x2 direction. Okay. Is this clear? So, now let us try to write the equations of this flow. And let's also assume that it is given to us that mean of U3 is 0. I'll probably not need this, but anyway, it's just mean flow is only in the U1 of x2. Now, if we use the continuity equation for mean flow, we get du1 by dx1 which all of these are 0. First and third are 0 because the flow is homogeneous in x1 direction and x3 direction. So, and this implies that mean of U2 du2 by dx2 is 0, but mean of U2 cannot depend on x1, x3 because the flow is homogeneous in x1 and x3, cannot depend on time. So, therefore, mean of U2 is equal to constant, and that means it has to be equal to the suction velocity or the velocity which is coming in at the wall. Because at y is equal to 0, mean value of U2 is Vm. Instantaneous is Vm, but that is constant, so its mean is also Vm. Okay? Is that fine? So this is the continuity. Always, whenever we'll use equations, we'll first use the continuity equation to simplify things. So now what we know is mean of U2 is a constant. Giving this information, I will move into the Navier-Stokes equation. And this is, if you have done, we do this for laminar flows also, but this is slightly different because now we are using it for the mean velocities. So we use the same, it's exactly like what we did in the exact solutions in the first course. But we are applying this information on mean. So now, what is our, let's look at the mean momentum equation for this flow in the one direction, because in two direction everything will become zero, three direction everything will become zero. And of course, when I write pressure, gravity has been clubbed with the pressure term. So I'm not. Now the mean momentum equation in the one direction will become एक मिनट. Yeah.
Why haven't we taken gradient with respect to the three direction?
No, because they are zeros. It's homogeneous in x3 direction. So when I take gradient with respect to the x3 of any quantity, that will be zero of the mean quantities. See, I will get mean of u3 du1 by dx3. So I'm coming to that. I'll make it zero. So what you are saying is I should have added this term. Okay, let me add this also. Yeah.
What allows us to assume that the pressure gradient is zero in all the
Oh, that is prescribed in the problem. Because we want to show the effect of scales, what the velocity scales do. So therefore, I have taken it. Maybe you can think. Normally, see what happens is it is something like you think of as a Kuwait flow problem in which the pressure gradients are zero. The flow is being caused only by the pulling of the plate. So in a mean sense, that is what is happening. So now when we write this, du1 by dt is zero, the flow is stationary. This term du1, u1 is not zero, mean of u1, but du1 by dx1 is zero. In this, u3 is also given to be zero, even if it is not zero, du1 by dx3 has to be zero. So this is there. And so what we get is now this mean of u2 I can write it as v sub m. What I get is vm du1 by dx2 is equal to nu times, or is equal to, let's write it as d by dx2 of nu times now actually while writing this term I have also simplified, because there will be another derivative d by dx1 of u1 prime u2 prime, but that has been taken as zero because of homogeneity. And similarly here there's du2 by dx1. D mean u2, but mean of u2 is constant, so therefore that also becomes zero. So they have been written like this, okay? So now what I can do is I can integrate and I multiply by rho. So what I get is rho times Vm times mean of U1 is equal to mu times so it's just a simple d by dx2. So all I have to do is just integrate between the limits. Now what we have to do is at x2 is equal to 0. Now when I say wall, I'll only mean the lower wall. Upper wall we realize is just there to cause the flow. So at the wall at x2 is equal to 0, we define the wall shear stress in terms of so this mu u1 by dx2 is what? It is the shear stress at the wall. The average shear stress or the shear stress due to the mean velocity. And at the wall, we write it as rho u star square. So we are using that as a definition of u star. It is written in terms of the shear stress at the wall, and u star is called the friction velocity. And you see the dimensions, u star will have dimensions of velocity because rho u square is the same dimension, that's the stress, pressure. Rho u square is the pressure dimension is equal to mu times du1 by dx2. So this is a standard thing which is done, that we define the shear stress at the wall as rho u star square. So this is something which in some sense gets prescribed because of the mean velocity. Okay, so this is called the friction velocity. So now in the right hand side here, we have mu du1 by dx2 at x2 minus mu du1 by dx2 at 0. So this we will write it, at the second term will be written as minus rho u star square. Okay, now far from the wall, we will assume the laminar shear stress is very small. See, we have two limits, one at 0, one at x2. So the upper limit is away from the wall, and there we will assume that the laminar, or I should say average shear stress, laminar may not be the right word, laminar or average shear stress is shear stress coming because of the mean part, that is very small as compared to the turbulent stress. So this will be assumed to be 0 at y is equal to x2. Now, what is the value of the average stress at the wall? What is U1 prime at all time at the wall? 0. What is U2 prime at all time prime? It is 0 because the fluctuations also follow the see, average values are all 0 and instantaneous are all 0. So when you take a difference, so the fluctuation, except of course average of U2 is not 0, it is equal to Vm, but average of U2 prime, or not average, U2 prime at all instants will be 0. U1 prime at all instants is 0. So when you take the average of U1 prime, U2 prime at y is equal to 0, what will you get? 0.
I'm sorry, why is the average independent?
What is U2 prime? Vm. And no, what is U2 prime? What is instantaneous U2 at the wall? Vm. And what is mean of? That's also Vm. So that means irrespective of turbulence at the wall in any flow, U1 prime, U2 prime at x2, the average of this has to be equal to, this is equal to 0 because U1 prime is equal to 0, U2 prime is equal to 0 for all t or for all realizations. This will be for everything. This is 0. So now what we get is, if I apply this in the equation, Vm times mean of U1 is equal to so now I go back to this equation. So this equation at 0, mean of U1 is 0. So this just becomes rho Vm times U1, implying it is U1 at x2. This will be equal to, now this term, the top limit is 0. The bottom limit is minus rho U star square. This one, the top one is rho U1 prime, U2 prime. The bottom is 0. So put all this in and you are left with this. Vm times U1 is equal to minus U1 prime, U2 prime minus U star square. Okay. So now let us first look at case 1 where Vm is 0. Now we realize when Vm is 0, there is only one scale in the problem, the mean velocity. There's only one velocity scale in the problem, which is coming, or you can think of it as a time scale as dVm by dx2, 1 over that. So that will be a time scale. So there is only one scale coming from the mean velocity gradient when Vm is 0. Okay. So now let's look at this case. So here what you get is minus U1 prime, U2 prime is equal to U star square. And this is at all x2 where the viscous stress or the laminar stress is negligible. Yeah, they are negatively correlated. That we have already discussed. I think we said that the coefficient between U1 prime and U2 prime is a negative correlation. So, okay. Now, so that means this actually u1 prime, u2 prime was supposed to be a function of x2 because it is 0 at the wall. But what we find is in this layer where the viscous stresses are negligible. So that is why this will not be very valid very, very close to the wall. Because if you're just at the vicinity of the wall, u1 prime, u2 prime is 0 and the laminar stress is not 0. So the viscous stress is, but once you go slightly away from the wall, then this becomes valid and Reynolds stresses are almost, it is showing that it is a constant equal to u star square. Okay. So now this is called the constant stress layer, which occurs close to the wall. So what it tells us is that u2 prime RMS is independent of x2 and proportional to u star, and the one argument we have used here is u1 prime RMS. Because these two are well correlated, u1 prime RMS and u2 prime RMS are of the same order. So we can write it as either u1 prime RMS or u2 prime RMS. And so that will be proportional to u star and independent of x2 in this layer. So if we now look at I'll just continue for some more time. We'll talk of the second case, the suction case in the next class, but I'll finish this case today. So if we look at the vorticity omega prime, this will be of the order of u2 prime RMS upon L, and this will be u star upon L, and the vorticity, mean vorticity, is of the same order because the time scales are the same. So what we write it as alpha 1 this is mean vorticity, alpha 1 is a coefficient of order 1. So, or you can say we are equating the time scales. The time scale of the mean flow is equal to the time scale of the fluctuating flow, and the fluctuating flow, the time scale will be equal to u star upon L. Now, since there is no in the problem, if I look at it, there is no length. If it was a flow between two plates, then a length would have come in. But here there is, ये class तो नहीं होती, check कर लो अल्ताफ, class होगी तो होगी. Since there is no length scale in the problem, we take L is equal to so whatever is happening in the flow the only length scale we can find is the distance from the wall, which itself is a variable. So we get from here du1 by dx2 is equal to 1 over alpha 1 u star upon alpha 2 x2 And this alpha 1 times alpha 2, the product of two constants, we write it in a standard way as 1 over kappa. And there's a reason, because this kappa is called the von Karman constant. So now what you can do is you can integrate this and you get u1 is equal to u star upon kappa log of x2 plus constant. And this is what is called as the famous log layer near the wall. In any turbulent flow near the wall, whatever be the flow, you always encounter a region which is slightly away from the wall, not just at the wall, which is called the log layer, where the mean velocity varies like log of distance from the wall. And this, you do many experiments, many type of flows, you always find a log layer. And it turns out that this kappa also turns out to be more or less a constant in all these flows. Its value is something like 0.41. And this was one of the successes of the mixing length theory. And you can even, I'll show it in the next class, that this follows from, if we use a mixing length, we get the same thing.
We have gotten this result from the assumption that VM.
VM was, yeah, so this is obviously, so this is working only when there is only one velocity scale, the mean u. When there's a second velocity scale, which we will talk of in the next class, we will not be able to get such a straightforward expression.
More or less all the flows we get this.
No, yeah, but so we will show that. So this is, what I meant was without suction. Matlab, flow means flow in a pipe, flow in a channel. This was flow in next to a wall. You always get this log layer. And there's a form of log layer which even comes in flows with suction. But flows without suction, you always find a log layer. And more or less this constant is also almost universal. Okay? So I think hopefully at least today, I thought we are moving a bit more from the abstract realm to a physical problem. And we will continue in this in the next class with the when there is suction. And there we'll show we'll not be able to do this. And we'll have to again use some dimensional arguments to get to things. And then we have to use some experimental data.